All right, well, welcome to the now sunny Winter Star Party. I hope that everybody got to observe last night a little bit.
Yep.
Yeah, okay. We're kind of waking up. I slept in good, but had some nice observing till about 2 a.m. And I was tempted to take some fog photos, but I didn't quite get to it. I expect I'll be able to do that most evenings here. Those are always fun. So I'm going to talk, this is a little bit self-promotional today, just to kind of talk about when I make mirrors, why I do things a certain way that I do, and why I think that makes for a better mirror. And if you guys want to move in, I don't care, whatever. The closer, the better. I'm going to try to stand over here, so I don't know if I'm going to block the screen for you. So I still got to touch, change the slides. So the quieter I can talk, the better for my voice. So what I've got on the slide here, on the left, that's a 50-inch f4 cast cellular mirror that I actually ended up doing twice because it was damaged by a coater. I'm not going to talk about that part. And on the right, just for size comparison, I believe that's a 28-inch that is in another country at this point. And so that's kind of, that size range is where I specialize, and I go down to about 16 inches, maybe smaller for fast stuff. So we're going to talk about some of the things involved in making a large mirror. So the most common question is, how in the heck did I start making mirrors? I'm actually an electrical engineer by training and computer engineer, and I started doing it as a hobby. And I discovered, thank you very much, discovered that I kind of had a knack for it because I'm a scientist. I like to test things and test hypotheses and figure out how to make things work. So I started out with an 8-inch mirror kit from Wilman Bell back when I was in middle school in the late 80s. And I finally finished it in 2003 after getting interrupted by various, high school, college, having a job and all that stuff. It was an 8-inch f3.9 by the time I got done with it. And I still have it today. It's a fun little scope, especially with the night vision stuff like I was talking about on Tuesday. Did anybody here get to see the night vision last night? I know you did. You did? Okay. I couldn't tell in the dark, and I'm not sure. Pat, did you get to see it?
No.
Okay.
We're down to
It must, maybe tonight. Okay. So the main point from that talk on Tuesday was that fast mirrors and fast systems are better for night vision because they have a smaller image scale at the focal plane, so they put more photons into per area. That gives you a brighter image, not only for CCD imaging, but for night vision viewing as well. They give you a little more flexibility in what you can look at. So after I started looking at some other mirrors that ended up in my house and in my shop, I kind of discovered that I can do better than this, and maybe I'll start doing this on the side. And that took off, and in about 2006, I actually founded Lockwood Custom Optics, and then I incorporated later on. 2009, I went full-time making optics and stopped doing, I was doing acoustic signal processing research at the University of Illinois. But, working for somebody else and working in a pretty boring area, I needed something different, and I needed my own schedule. So my goals and my company's goals are to make quality optics for a variety of clients, amateurs, professionals, industry, educational, whatever. I'm not going to be priced at the top end of the market, but I'm also not going to be the cheapest because I want to keep quality up and pay individual attention to each optic. I don't think a lot of people realize the number of hours that goes into a mirror. It can approach several hundred depending on the size. It can be as low as 40 or 50 for smaller mirrors that I do. It takes a lot of time and labor and individual attention. And I specialize in faster optics. I've done f2 for various systems like the LiDAR, which is, they use a laser to bounce into the upper atmosphere, and they collect the returns with a big fast mirror in order to study what's going on in the upper atmosphere in terms of chemicals, wind speeds, and all those sorts of things. So that's a pretty popular area for me to supply right now. I also work on, through publications, talks, whatever, helping my clients get the most out of their optics, working on mirror cells, collimation, whatever. I try to educate people. Because if people aren't using my optics properly, I'm going to get blamed for the problems. So in 2009, I moved out of Champaign, Illinois, out into the country and bought a house that had a pretty good sized shop space that was located under the house. So It's on a concrete slab. I could heat it and cool it to a fairly constant temperature. That's really important for making optics, because when you have moving air, it causes issues with testing. Just like if you have bad seeing here, you can't get a good star image. If I have bad seeing in my shop, I don't get a good accurate test. So I'll talk about that a little bit more. Surprisingly, the thing I discovered, and I knew it was pretty far away from most heavy traffic and trains, which cause vibration. Vibration's also a problem for optical testing, because if you're doing interferometry, your fringes are moving like this. And I can actually see when somebody pulls in the driveway. If I have the interferometer on, I can see it shake. The most surprising thing that I didn't think of before I moved out there, and this is a rather tall house, is my biggest vibration source is wind. Living on the prairie of Illinois, we have a lot of wind. The wind we had the other day on, what was that, Sunday? That was nothing. That was a light breeze from Illinois. So it does actually shake the building, and that causes some issues with testing. There is room to expand, and this talk was written for Okie-Tex originally, so that starting in October still hasn't happened yet. I'm trying to build a shop addition to have more testing space in my old garage. So I took care of the air movement. This is what the shop looked like a number of years ago. I've got glass stacked up here. Now there's a computer here. This is a small grinding machine that I built just for about a 14-inch mirror. It mostly gets used to rotate pitch laps under heat lamps, so I can warm them up and press them onto a mirror. We've got a large machine that'll handle a 50-inch blank currently. We might be able to enlarge that to handle significantly larger, maybe a 75. There's another machine here that'll handle almost a 36-inch. When it gets this new turntable, it will. And this small machine back here used to belong to Dick Westling. It'll handle a 25. All of these back here, except for this one, were built by John Pratt of jpastrocraft.com or LLC. He builds telescopes, often with my optics in them, and he lives about 45 minutes from me, and he has a nice machine shop, so he's helped me out on a number of things I needed to do machine-wise. So this is how the shop was prepared. Anybody do spray foam in their house? Nope. Okay. This is the shop space before. I put up studs and then had it spray foamed. Not only from the outside, on the outside walls, but also the inside walls that adjoin the garage and a bit that goes around the stairway that goes upstairs to the living space, so that I could really isolate the space. And recently, I got, several years back, I had geothermal heating and cooling installed, which is a ground source heat pump. And I had that expanded into the shop area, whereas before it had been heated by a propane heater and it hadn't really been air conditioned. So now I have really nice climate control in the shop. It's a concrete slab, which is important for moving things around. Obviously, heavy things like machines and mirrors, so you can just roll them around. I have a rolling gantry crane that will lift 2 tons. The heaviest mirror I've done is about 1,400 pounds. That was a solid 50-inch mirror, about 8 inches thick. And the other key to concrete is it doesn't move much. So when you are set up to test interferometrically, things don't move too much. You still get vibration, but your distances aren't changing, which is also important for other types of testing like Foucault. And I can shut off the geothermal system, the heating and cooling, and I typically do that when I'm testing, depending on how critical it is, especially at the end, so I can have the air stabilized nicely. So the first step in making a mirror is for me to order a piece of glass, and typically it's usually machined to the proper tolerances, the right thickness. It's got a reasonably flat back, and it's got a nice concave or convex curve already diamond machined on the front, ready for grinding. When I get these, I take them out and I check them for strain. So that's internal stress in the glass. That basically, think of it as having a spring inside of your piece of glass if it wasn't annealed properly. So this test is with a polarized light source in the back. You can actually use a white image on an LCD monitor as a source. And then you put another piece of linear polarizer between the camera or your eye and the mirror, and you rotate that. And you see, as it darkens, you see how it looks. So in this case, if we had a perfectly annealed mirror with no strain, this would go gray. But what strain in glass does is it actually causes a rotation of the polarization of the light that's going through it, and that creates those light and dark areas when you view it with linearly polarized light. So this wasn't great, but it was a thicker mirror, and that was as good as they could do. So this is about the limit of what I'm going to accept for strain of glass. You have to sometimes accept what your glass company can give you if they can't give you anything better. And it turned out to be a fine mirror, so there's no problem here. It's tricky. It's sort of a judgment call. You kind of build up in your head a library of kind of what happened with various things in terms of different stress images. So here's some other ones. At the top, I think I'm rotating the polarizer from those top images to the bottom one, I believe. And in this case, we have somewhat of a cross, and that's not so good. It's acceptable, and this is pretty typical of a lot of imported glass right now. You know that a lot of glass is coming from Asia. It's being made and annealed over there. We don't know a whole lot about what it is sometimes. Sometimes it's BK7, sometimes it's borosilicate, or they claim it's Pyrex, not really sure. But often the anneal looks a lot like this, which is questionable. So what does this do to your mirror? Over time, it's possible, and I haven't had enough time to test it, it's possible that the mirror shape can change. I have seen some weird readings on imported mirrors that seem to change over a couple of weeks. Enough that I said, I'm not going to do this particular project, we need to make a new mirror. Sometimes it might be stable and be fine, but the most typical symptom is as it cools off, like your mirror's out in the sun all day, and then the night cools off, as you have a temperature change, that stress causes the mirror to go astigmatic for a while, until it sort of catches up with the air temperature.
What?
Astigmatic. We'll produce astigmatic images. So astigmatism is when the curve of the mirror is different across one axis than another, in crude terms. There are other distortions like that. But yeah, so you see stars that elongate this way and then this way as you go through focus. So if you see that, and it kind of goes away with the night, you may have some strain in your mirror, or else there's some other mechanical pinch due to temperature that's causing that. I have an article on my website called Why Aren't My Stars Round? That covers sort of debugging and figuring out what's going on, diagnosing what's going on with a telescope. So if you start to see color in that test, you have really bad strain, and you don't want to deal with that piece of glass for a precision optical purpose. So back to concrete, the glass is a lot like the foundation I was talking about in the shop. That's what the shape of the mirror is based on, obviously, and that's what's important, is the shape of the optic when it gets done. So when that piece of glass comes in after I strain test it, I'm going to check its dimensions and kind of keep an eye on it as it spins on the machine and make sure it doesn't have too much wedge. That would be a variation in thickness. For a competent glass supplier, you're not going to really be able to measure any that's significant, and up to a small amount, it doesn't matter for reflectors. It does matter for lenses because light goes through them, and if they have wedge, it's going to act like a prism a little bit. But in my case, I just want a good machining job that gives me approximately the right curve, a pretty good, mostly flat back, a nice bevel to keep the edges from chipping, and that's about it. So I start my work on the back of the mirror.
Can you put the bevel on yourself, or do they have to do that before you get it?
I can put the bevel on, just spinning it, and you can hold a diamond hone against the mirror. And sometimes I increase the bevel if it gets too small, depending on how much I've ground off. Yeah. So to test a mirror and to work it, it's usually sitting on its back surface, at least to work it. Most of the time when we test it, it's up on edge and it's partially sitting on its back. But we want that thickness to be as uniform as possible. We also want the back of the mirror to have a pretty smooth finish in order to allow it to move around on the mirror cell contact points. So we don't want our mirrors to stick to things, because generally that's going to warp the glass and give us bad images. So ideally it's going to sit on its rear supports, and you'll be able to spin the mirror easily in the mirror cell so that it's not binding on any of the points. So I fine grind the back of pretty much every mirror that I make, depending on some of the cellulars you can't do. But for any monolithic blank, I'm going to grind the back. So this is how a mirror blank is generated on a mill at least. This is a round diamond tool, has a rim of diamond, and if you tilt that, depending on the tilt angle, and you rotate that mirror, that's an old mirror that's got a very ratio being generated to a shorter one. If you tilt that and then you rotate the mirror underneath, you produce a spherical surface if the tool is big enough. If you have a larger mirror, in this case I think the mirror is bigger, the tool doesn't span half of its diameter, so we have to do it in steps and carefully control the angle to make sure the surface comes out right. But that piece spins, the mirror turns slowly underneath, and coolant is put onto the mirror, and through that method you can generate a curve in the glass itself. So this is what I typically have a glass company do, but sometimes you have a blank you need to use for something else, or it's a bad mirror, and we'll just start generating. As you can see, the coating's still on it, but it's going to go to a deeper curve. So if you can just see these arcs are the damage path left by the grinding of the diamond tool, and that is something that needs to be removed on the front. On the back I want to get through most of it, but it doesn't really matter. On the front, that could cause pits, that could cause surface defects, a large number, and we want to avoid as many of those as possible. A mirror surface is rarely perfect. Sometimes you hit a small bubble or a small defect. It doesn't really matter, but this sort of internal damage we want to get rid of. So on the back, I'll do a shorter grind, typically 3 or 4 hours, go through the grits, and I'm looking for, I think I have a photo coming up here, there we go. I'm looking for the whole surface to be grinding uniformly. Now what I started out doing was I put marker lines across the back of the blank, and I started grinding either against a flat tool or the back of another mirror. And as you can see, it's ground away here and here. And that means the mirror sort of has a saddle shape, which is astigmatism on a large scale. Now we're talking about a few thousandths of an inch, or maybe more in some bad cases. A lot of times what happens is the glass company will machine the blank and then anneal it, and it will change shape due to the strain, the internal strain, and I'll be left with something like this that I have to grind for an extra hour or two to get rid of. But the point is, if the back of your mirror is not ground, it may not have a regular shape, and it also will have more friction against the mirror contact points on the rear because it's more roughly machined. So ideally, we get a nice smooth figure of revolution on the back. That means it doesn't have to be perfectly flat. It could be slightly concave or slightly convex, but it's got pretty much the same curve no matter what axis you look across. And I just covered most of those reasons, so I can skip that. Now I start working on the front of the mirror, and it's likely that the front has the same type of distortion as the back, because the whole disc will move around as it's annealed. Or possibly there's a little variation in the rotary table that it's being turned on in the generator or in the generating rig. So we're talking thousandths of an inch, but it's still got to be removed. So I'll grind. I start off with 50 micron. That's about, what is that, a thousandth of an inch, 2,000ths of an inch grit size. Very small, but I can remove a lot of glass over time with that and not cause a lot more damage that goes down into the glass. Has anybody made a mirror here? And you've worked with carborundum. I hate carborundum. It's evil stuff. It's got big grains, it sticks to stuff. I just don't use it. I start off with 50 micron aluminum oxide. It's a white powder, it's nice and clean, and I just grind away. And I just keep squirting grit on for hours until I get down through most of this damage. And then I'll go to, I'll also be watching that saddle shape is gone. I'll take the tool off, put some more lines on, grind it some more, because what a lot of people don't realize is that saddle shape can persist through into polishing, and then you've got astigmatism you've got to remove in polishing. Might as well get rid of it as early as possible. It happens though that mirrors come through grind with astigmatism that I have to polish out. That's just another test you've got to do in order to make sure you can get rid of it. So then I go to 40 micron, 25, 12, and sometimes 9 micron. And you don't always have to clean these up like you do with your typical ATM hand grinding. So if it's running on a machine, you just keep squirting on grit, and it keeps going lower and lower. It drops down into your pan. You clean up every now and then. And as long as you are careful about what you're handling, you generally won't get scratches with this sort of machine work. So it does save some time compared to what hand grinding is. At the end of fine grinding, you get a nice low angle reflection. This is a 36-inch that I made for Warren Rupp Observatory after their 31-inch had an unfortunate accident. We were able to enlarge the telescope, but that was a nice view of the low angle grind after maybe a 12 or 9 micron grind. And you can just let it go for a while. It's not going to hurt to do a bit of extra grinding. You actually want to make sure you're removing the damage from the previous pits. Typically what I do is I look at the surface with a loupe, a magnifier, and look for abnormally sized pits. And after a while you get a feel for what should be there for a particular grit and what shouldn't. And if I see anything funny, I keep going with that grit. Again, sometimes I hit a bubble I can't grind out because it's just too deep, and that's just the luck of the draw with glass. The bigger the mirror, the more chance you're going to hit a defect that you can't remove. And it doesn't harm images, it only harms my pride, and the customer might comment on it, but at the price level I'm working at, I can't have the mirror regenerated and make it even thinner, which often can cause its own set of problems. You just have to accept a defect here and there. Sometimes there are defects you can't get through. There's a long, thin bubble or something that just ends up intersecting with the surface. It's the nature of Pyrex and borosilicate glass in general, made in large sheets. So at this point, I'm going to look for scratches and other defects and kind of note them. A lot of them will go away during polish, because not only do I have to polish all of the pits away from the grinding, I then have to polish the right shape into the mirror, which means I'm going to be removing quite a bit of glass from the center of that optic in the process of parabolization. This would be a shot of me polishing a 1.1 meter mirror with a lap on top. The bottom piece is turning, the mirror is turning face up, and on top there's a pitch lap that will spin just due to the bottom piece spinning, and the arm is slowly moving in and out over time to help blend and create a uniform polish. This is on the large machine, and I've got a line up here to every now and then cerium oxide is pumped down onto the mirror surface, and I can typically let these run for a couple hours, maybe 3 hours, before I have to look at the pitch laps and see how they're holding up and maybe do some maintenance on them. So this is the process of removing pits from grinding, and then at the end of this I'll be testing to make sure I don't have any significant astigmatism, and if I do, I'm removing it. That's one test that a lot of optical shops and opticians may sometimes, well, let's just say skip or execute not properly, in my opinion, and astigmatism can get by small amounts. So I try to get it down to a reasonable level. We're testing a mirror up on edge. It's going to bend a bit. We have to rotate the mirror and look at what sort of astigmatism we have, and if anything rotates with the mirror. It can take extra days to do that step, and that's an important step. So we talked about this a little bit. Get rid of all the pits, polish evenly over the surface. Because typically a mirror won't polish evenly. It may polish at the center a little quicker than the edge, because you're trying to match the wear of the polishing to the shape of the mirror, and the pitch flows a little bit. So you can actually control the radius very tightly in polishing if you need to, depending on the requirements of the project. Typically with telescope mirrors, we don't care about getting a precise focal length unless we're making a casa grain, and we need to have the mirror spacings defined ahead of time. So we get rid of astigmatism, and now we move on to a little bit of testing. Just for perspective, these are what pits look like, unpolished areas. This is a blank that I received to rework, and I've got a microscope, a very bright microscope illuminator hitting it at the side, and you can see where it hits the interface of the glass. You see all these sparkly little bits, and those are pits that someone else should have removed, either in polishing or probably they didn't spend enough time grinding a particular grit. If you take your Foucault tester and you swing the knife all the way through the beam and block the direct light, you get the scattered light back. And this is that mirror. You can see each one of these little things is maybe multiple pits that are scattering light, and that has to be fixed. So I reground that mirror. For an astigmatic mirror, One way to test for that is with an interferometer. In this case, I'm trying to remember what mirror this was. Now, this is actually Tom Clark's 42-inch, partially through rework. It had about 3 waves of weird irregularity, and I just started polishing until it was all gone. It took many days to actually get rid of it. Test, work to remove some astigmatism, test some more. So in this case, we have these areas are high, and these areas are low, and it was by a couple of, actually over 2 waves at this point, and I kept going. Astigmatism shows up in the Foucault test. Who's actually done Foucault testing here? Anybody? A few of you? Okay. So if you ever see something like this, additionally, you can see these pits. You can see these little marks as well. This is with the knife edge in the normal testing position. I didn't swing it all the way through to just see the pits. You can see the shadows, but if you notice, there's asymmetry here. This shadow should be symmetric along a line here. So what this tells me is that somewhere not aligned with this axis or this axis is the axis of astigmatism. So it's either astigmatic somewhere along this line or somewhere along this line. You have to have astigmatism rotated with respect to the knife edge in order to see it with the Foucault test for those mirror testers here. But if you haven't done that, if you see that kind of shadow, that's not good. That means there's a lot of astigmatism. Another test that I have is a very small laser pinhole that I use as an artificial star. It's a quick test for figure of revolution. In this case, there was a machine running at a repeated ratio, so I got a 5-sided asymmetry, and that mirror got refigured. In this case, this was a very, you should see a point here basically. You should see a bright point surrounded by rings. This is a very irregular mirror. I think that may have also been a test image from the 42-inch that Tom had. So what we want to see is a bright point. That's a quick test, saves some time over interferometry, kind of just basically a time saver. So how you fix it, you polish more, you work on the high areas by various techniques, and keep testing until you can't really detect any significant astigmatism, or it's a reasonable amount for a large, thin mirror. Gravity is a pain in the ass. You mostly test a mirror up on edge and it wants to bend in potato chip, depending on how you have it edge supported. So all I'm going to say is that over the years I've learned a few things about how to support mirrors on edge, typically not in slings because they have their own type of distortion, and I've gotten very good at detecting astigmatism. I'm going to leave it at that so that I keep people awake here. We see some unusual distortion. This is a mirror that I actually used at the Winter Star Party a number of years ago down in the Keys. I think it was 3 years ago. The star test looked like a wagon wheel, and we weren't sure what was going on. But when I actually used the interferometer to test it, you can see it has 7 high areas that show up on the 3D plot here. And I don't know how they did this. I have no clue how you produce a mirror that has that, unless you have some really bad luck. And when I polished, I decided to polish off the coating. Sometimes I do that just because it saves a little bit of time, and it can lead to interesting pictures like this. You actually see these high areas when I put a white piece of board there to provide some contrast. So you can literally see the high areas polishing off first on that mirror. That got repolished, refigured, and okay. We're doing something to the camera? Okay. This was polishing the Clark 42, and what looks wrong to you?
It's off center.
It's off center. That shouldn't happen when you polish off a coating. So that was that weird asymmetric 3 waves of something or other that is now gone. A few of my competitors. So as I said, it can actually take days to get rid of astigmatism or other distortions. In the case of the Clark mirror, I think it was about a week. But in the process, you're also polishing through any defects that are left in the glass, and you're going to have a very nicely polished surface unless somebody did something horribly wrong in the grinding process. That's enough. I spend a lot of time on astigmatism, others don't spend enough. So, at this point, if we've gotten rid of the astigmatism in the pits, we're pretty much done with rough polishing, as we call it. That's the purpose of it, to get rid of those things. And it's going to be somewhere near a spherical mirror, or spheroidal, if you want to use the proper geometrical term. And typically, if you're going to let something spin on top of something else in terms of grinding surfaces, those surfaces are going to start to match, right? I don't know if anybody's ever done machining or scraping plates or anything like that. But typically those surfaces eventually will start to match. And they're going to generate what's roughly a sphere. So that's what we get roughly out of grinding, depending on where the grit's sort of accumulating. And ideally we get almost a sphere out of polishing. But what I'm really looking for is the outer part of the mirror. I don't want to have a nasty rolled off edge. And if I have a little bit of what we're going to call correction, which is spherical aberration already in the mirror, that's actually a good thing. That can save me a little bit of time because I need to actually polish in more of that to make the mirror a parabola. Figuring is the process of taking that mirror that's a good figure of revolution and maybe already has some parabolization in it and turning it into a precision optical surface. Now, sometimes you want to make a sphere, in which case you do things a little bit differently. Sometimes you want to make an ellipsoid, which is somewhere between a sphere and a parabola. And sometimes you want to make a parabola. Sometimes you want to make a hyperbola, which is beyond that. But basically, mostly what I do is I take a spherical surface, if you just visualize this as a uniform curve, and I make it gradually deeper in the center. That's the shape. It has a little bit deeper, has a little bit shorter focal length in the center than it does at the edge. And that's what allows Foucault testing to work. You can actually measure that. Sometimes for a really aspheric mirror, one that's got a lot of this to it, you can actually grind very gently with fine grit that into the center of the mirror and help you remove glass faster. Because polishing removes glass fairly slowly, on the order of a wave or two an hour. And if you've got to polish or grind in 200 waves of asphericity, departure from a sphere, that can take a while. But sometimes it's a good thing. It all depends on many variables. But you can grind in. And the trick is, after you've ground it in, though, is maintaining that shape. The larger shops will do that with very expensive automated polishers that have very sophisticated pressure application devices on a polishing head, like these guys at the Mirror Lab that make the 8-meter mirrors. They have very complex machines, and they will grind in most of that shape and then polish it, and then tweak it. Whereas I mostly polish it in. So we've got this polished shape on the glass, and I've talked a little bit about testing, looking for the figure of revolution, lack of astigmatism or other weirdness. And I've talked about using interferometry and an artificial star test. For Foucault, the knife edge test, what you're actually doing is measuring across one axis, the horizontal axis. So you can rotate the mirror and test across different axes and see if you get different results. That's another way to test for astigmatism. But what I find is that for the mirrors that I make, Foucault produces the most accurate measure of how much correction or parabolization I've got in the mirror. So far, it's been more accurate than interferometers that I have, because I'm not setting up, I don't know, I'll go off here just for a second. I'm not using autocollimation, which is a flat mirror, because that introduces another mirror that can bend under gravity, and it introduces a whole other, many other sources of errors that can cause things to get very frustrating. So I find that the simplest test is best, which is Foucault, at least to measure the correction and how close I am to a parabola. Now, if I'm measuring across one axis, and if I have a good figure of revolution, what should I get when I measure across the other axis? Same readings, and usually I do. So under that condition, Foucault is very accurate, is my point. A lot of companies will cast dispersions upon that test and claim that it's an amateur test, but in reality it was used to mostly finish the 200-inch Hale telescope. Way back when, they did a pretty good job. There were other tests used as well, but it's very accurate for our purposes here. So the other thing Foucault shows is roughness. If you can see, there's some dirt, there's some funny, probably water stains. And you can see this little bit of texture. Can you see that on this mirror? Okay. Whereas this one, other than a few JPEG artifacts, it's much smoother, and the shadows are very smooth and even. And if you notice, we have pretty much symmetry along, along this axis, but this line is very even where they meet. We can also see really bad roughness. This is what happens when a coder uses nasty chemicals on a mirror. It turns it into that sometimes. Really nasty stuff, or they leave it on too long. We can also use an almost spherical mirror or a spherical mirror to do Schlieren testing. Anybody ever done that? Looking at air currents, air movement? Okay. So this was actually looking through a mocked up mirror box. I did talk about this at Okitex a year or two ago, with fans, and you can actually see the heat plumes coming off the fans after they've been turned off. So that's heat coming out of the motors of these cooling fans. But this is the sensitivity of the knife edge test of Foucault. It's all the same test. So in theory, I finished the mirror. It tests out well. It's got good figure of revolution. It's got good correction. I clean it up. I cover it up. And into a crate it goes. This is the 50-inch being lifted with a spreader, a large metal piece that lets me put straps underneath in 2 places and safely pick up. This 50-inch mirror was only about 500 pounds because it was cast cellular. I also have a little, it's called a sky hook. It's a crank hoist that I can use to lift mirrors on and off the large machine. And those are safe ways for handling glass. That's what I do quite a bit. I can lift up to about a 30-inch mirror and carry it around if it's at waist level very safely and put it on a cart, or put it on a cart and roll it around. But for the larger ones, you need equipment like this to do it safely and to do it by myself. For testing a large mirror, typically we don't have a tall structure to test it in vertically sitting on its back. I may actually do that someday because my house is rather tall, and I could actually cut a hole in the floor above and test down through off of a scaffolding. I may have to do that someday, but for right now, I'm going to try to avoid it. So in this case, this 50-inch cellular mirror was supported on its edge by a sling, but it was a carefully applied sling. These blocks of wood apply the pressure where the ribs are within the cellular structure. And this actually turned out to work extremely well for this 50-inch f4 mirror that is now at my friend Bob Holmes's, the Astronomical Research Institute, and he uses it to measure asteroid positions for NASA. So he has a 50-inch, a 32, a 30, and a 24, and sometimes he runs telescopes in South America. So that's where this 50-inch went to. It's only about an hour from my house, but it turned out very well. The cast-in ribs provide the structure that keeps the glass disc rigid and allows it to be sported on edge. This actually, on edge, worked better than a lot of typical monolithic blanks or blanks that are solid glass. So a couple of little differences. When I'm polishing, the table's turning pretty fast underneath to turn the mirror, and the arm's moving very slowly. For figuring, it's the reverse. The table's turning rather slow, and the arm's moving quickly, pushing the pitch slap across the mirror, maybe somewhere between 6 and 10 strokes per revolution of the mirror. But you want to make sure that that doesn't repeat. You don't want to have the pitch slap hit the same spot at the edge of the mirror each time the mirror comes around, or else you get that 5-sided weird image I showed earlier on with my artificial star test. So for polishing, you generally have a bigger pitch slap. For figuring, they start out sort of large and get smaller and smaller as you get closer to the right shape and you start working on smaller areas and the center. He's up here, Lynn, if you need Tom. There are other ways to do it, but that's how I do it. So this is what figuring looks like. This is an 18-inch aluminum pitch lap substrate. There's pitch here on the bottom on top of a 50-inch mirror doing some polishing. And this is an 8-inch lap on the same mirror later on when I'm just working on a small high area. And I've also got, these are weights. on a cantilevered arm to help take some of the arm weight off of that lap. That arm weighs about 20 pounds. It's pretty hefty. I covered some of this already. I'm going to take final readings with Foucault to verify correction. I'm going to carefully double check the radius of curvature of the mirror. Why is that important? Anybody know? Everybody awake? I'm trying. Yes?
You're doing a Foucault test in both the diameter and radius, you have to know that.
Yep.
Very precise.
You have to know, to get accurate results with Foucault, you need to know the radius of curvature of the mirror. By the way, that's twice the focal length. And I also have to tell the telescope manufacturer what the focal length is, and I usually engrave it on the back of the mirror. So that last little measurement, I often see errors made in that. And that's one of the last things I do. I verify I've got the right measurement. I verify I've got the right measurement in my analysis program. And then I can put a very precise focal length on the back of the mirror and engrave it and make note of it. I'll do final figure of revolution checks after figuring, just to make sure nothing went wrong in the figuring process and I didn't get astigmatism or something else weird happening. And then I will put it on the machine, I'll center it up, and I scribe in a very precisely centered set of circles that mark the geometric center of the blank. Now, the faster you get, the more important it is to know where the exact center of the mirror is for collimation purposes. So these are permanent. These are actually made in the glass. This is an uncoated mirror with a bridge and a diamond scribe, and they look like this after they're coated. They show up very nicely, and with a well-machined blank with almost no wedge in it, that is the optical center of the mirror, as well as the geometric center. So this allows you to put on your choice of hotspot, whatever center mark you want to use, cat's eye, whatever, and then very accurately collimate the telescope later on. Right before I put the cover on the mirror, the protective cover, it's made of acid-free paper with cardboard on top. It's a specially made lid that Carl Zambuto started doing it that way, and I said that's a great way to do it. I'm going to do it that way too. I just do bigger ones generally. I'm going to look at the surface with a bright light. I'll use my microscope illuminator to look at a few places from the center to the edge and make sure I don't see any pits, nothing that I missed. I'll take a bright light and look for scratches that are obvious. There are always little microscopic defects on a mirror, and you can spend a day literally inspecting a mirror, but it's not necessary for this purpose. Then I will cover the mirror, flip it over, engrave a serial number, and take a picture of it, because people have tried to forge mirrors by other opticians, and it's got a unique serial number. I keep track of everything. I keep the pictures. Flip it back over and pack it safely in a crate. And okay, I don't have any pictures of crates. And we're about 15 minutes to go, so I can cover mirror packing if you guys want to and you're awake. I'll talk a little bit about that, but right now I'm going to just stop and take questions before people forget if they had a question. Yes?
How do you spec accuracy?
That's a good question. Typically for amateurs I don't, because there's way too much debate online and too much conflict that's created by actually giving test results. I am actually in the process of purchasing a new interferometer that may allow me to do that at some point after I come up with a test methodology, but that will cost extra.